Okay, we are recording. So let me hand the floor over to group 435K.
Awesome. Thank you, Dr. Trom. So hello, everyone. We just want to say thanks for coming out to our final presentation. Again, we're group 435K, and our prototype design is called the Solar Pill. Our group consists of Alexandra Canul, Minjae Kang, Dana Kendall, Robert Oglesby, Carlos Ortiz, Jose Rivas, and Maxwell Schreiber. Before we begin, we'd just like to ask that all questions be held until the end of our presentation. In the case that your questions get answered in a later slide, we'll also have slide numbers on each slide. So if you'd like to write this number down so that you remember which slide your question was on, we can go back to it at the end of the presentation. So with that, we first wanted to talk about our Hedgehog concept, our main design focus. To generate a Hedgehog concept, this is basically a combination of what you're passionate about, what you can be best at in the world, and what drives your economic engine. For us, we're passionate about 3D printing. We are best at creating compact designs. And what drives our economic engine is saving material cost. This ultimately led to a main design concept of design for 3D printing. To give an overview of our product, we have some general specs here. Our product has a maximum volume of 9.1 by 6.1 by 9.6 inches. This is with the mirror oriented vertically upwards. The mirror itself has a width and length of 6 by 9 inches respectively. There are two sets of planetary gears, as you can see in this picture, with each having a gear reduction of 4:1. The range of control and the azimuth and elevation angles are 360 and 180 degrees respectively, and the step accuracy is 0.45 degrees, meeting the customer need number 4. Within our prototype, there's a complete protection of the motors and gears from particulates, as they're housed inside the unit itself. And this design is also easily scalable, especially in terms of its controls, to a larger size and larger field of heliostats, which we'll go into more detail in later slides. Now, what makes our design stand out from all the rest? Well, we wanted to point out two main things or key features that directly relate to our Hedgehog concept. Our first is that all parts of this heliostat outside of the fasteners and electronics are entirely 3D printed. As you can see, some of the parts here on the left that were taken during our printing process. The second key feature is that this design is compact. The main body volume of just the pill portion itself is 9.3 by 6.5 by 4.7 inches. Now you may wonder how we get this design to be so compact, and we mainly accredit this to the compact design of the two planetary gear assemblies. So we'd like to show you these now so you can get an idea of how they work. The first one is the upper assembly with the arm that turns the mirror. And this one on the right is the bottom assembly that controls the azimuth direction.
Now we're going to go through the design evolution of our heliostat. On the screen, we have a visual progression of our model going through the various design changes we made throughout the semester. The most visible changes are the shapes of the cowl and side attachments and the mirror attachment method. Our first design evolution included the gear design. We knew that we needed to have enough gear reduction to achieve the 0.5 degree accuracy required in the customer needs. We wanted to keep the reduction reasonable so that the heliostat would still be mobile in situations such as going through the homing sequence and going to the danger position when needed. Since the NEMA 17 motors divide a full rotation into 200 steps, we found that the gear ratio needed to be at least 3.6 and therefore decided a 4:1 ratio would be our goal. To get a 4:1 ratio, we were mainly deciding between a harmonic drive and planetary gears. We modeled and 3D printed prototypes of each system and found that the planetary gears were more reliable and our team was more familiar with the system. So we decided to use planetary gears for both axes of our heliostat. Within the planetary gear system, the sun gear is the input and the ring gear is the output. The motor drives the sun gear in the middle, so the motor shaft can directly drive the gear. The planetary gears rotate around stationary axes to eliminate the need for a planetary gear carrier and reduce the number of parts. The ring gear was merged into the moving parts, such as the arm holding the mirror, to also reduce parts. After eliminating corresponding terms, after eliminating corresponding terms and rearranging the equation, we found the number of teeth for the ring, sun, and planetary gears were calculated to reduce the 1.8 degree step size of the NEMA 17 motor to a step size of 0.45 degrees and meet the customer need. Our next design evolution included the minimization of parts. This included the reduction of parts through the planetary gear design, as well as the cowling attachments. Our first design needed the use of 3 nuts and bolts for each cowling to secure it to the main body of the heliostat after being held in place, which required a substantial amount of handling and insertion actions. The design was improved to slide onto the main body using a rail to constrain the movement of the cowling using only one action. This change also made the cowlings more suitable for 3D printing, reducing the need for support material.
During our design process, we placed a large focus on predicting and preparing for the forces which the heliostat is expected to experience during both normal operations and extreme conditions. To this end, we approximated the drag which the heliostat would experience during the worst case operating conditions. These conditions were defined by the highest wind speeds ever recorded at McCarran International Airport in Paradise, Nevada, which were gusts of 90 miles per hour or 40 meters per second. Our initial designs performed rather poorly in terms of drag, with our earliest design seeing drag as high as 78 newtons. To minimize these forces, the design was modified to include fillets and general profile reduction to minimize cross-sectional area. To determine the drag coefficient of the modified heliostat body, the pill-like shape was approximated as a prolate spheroid, with a dimensionless drag coefficient being calculated based on body geometry, orientation, and projected atmospheric conditions. Using this approach, the drag of the finalized heliostat was determined to be 4.1 newtons. This indicates a force reduction of more than 74 newtons over the course of design optimizations. However, it's important to note that this is a rough approximation which fails to take into account the presence of the mirror, which in most configurations will significantly modify the pressure distribution and as such the drag. Furthermore, a prolate spheroid is an imperfect approximation of the model and will likely exhibit less drag than would practically occur. The mirror drag was calculated by approximating it as a two-dimensional flat plate. Using this model, the maximum drag produced by the mirror was calculated to be approximately 44 newtons. Once again, it's important to note that this is significantly larger than the actual projected drag, because in practical operation, the body will disturb the flow and pressure distribution around the heliostat. Using these worst case scenario values, the minimum cross-sectional area for PLA supports to survive was calculated to be 0.0026 square inches. Due to our design making use of supports with cross-sectional area of 0.058 square inches, we do not expect failure to occur in the supports due to the rather large factor of safety of 22.3. The mirror drag was also used to verify that the method of adhesion would be sufficient to ensure safe operation. The adhesive we selected in this design was Loctite EA E60HP, which was chosen primarily for its excellent adhesion to plastics and low cost, as well as familiarity among the group with this particular adhesive. This adhesive has a maximum shear tolerance of 13 megapascals, which leads to a necessary mirror contact area of 0.0026 square inches. And due to the actual mirror contact area being 54 square inches, failure is not expected to occur due to the adhesive, thanks to a rather healthy factor of safety of approximately 21,000. As we mentioned previously, the preliminary drag calculations made some very substantial and incorrect assumptions. So as the model progressed to allow for more careful analysis and validation of results, especially in preparation for wind survivability testing, which will be discussed in a moment, computational flow analysis was performed using SOLIDWORKS FlowSim. The first configuration examined was the maximum drag configuration with the mirror-oriented windward. This configuration saw a body drag of 19.2 newtons and a mirror drag of 32 newtons. This mirror drag is approximately 75% of what was predicted, which is excellent. However, unfortunately, the body force is nearly 5 times larger than projected. Thankfully, because the mirror supports are the thinnest and most sensitive components of the design, with the body being designed to be much more robust, and thanks to large inbuilt factors of safety, failure is not projected to occur in this circumstance. The next configuration examined was the mirror-oriented leeward. This configuration presented a mirror drag of 10.7 newtons and a body drag of 26.3 newtons. With a further reduction in mirror drag and a relatively minor increase in body drag, failure is not projected to occur in this circumstance either. Finally, the emergency configuration was tested. This is the configuration which will be utilized when extreme weather conditions are projected, such as when an incoming storm is detected. This configuration unsurprisingly saw the minimum drag of any configuration tested, with the mirror producing a drag of only 4.3 newtons and the body producing a drag of 14.2 newtons, both well within safe conditions. Given that this configuration may be set in approximately 6 seconds, and that the forces experienced produce stress well below maximum safe operating conditions, the heliostat is not projected to fail under any predicted conditions.
The wind survivability test was done to check whether our heliostat structure would survive under normal and extreme wind conditions in Nevada. The initial test that you see in the bottom right is the normal working condition with wind speeds of 4.1 and 5.3 meters per second using an industrial fan. Then on the next video on the bottom left, the heliostat is under extreme wind conditions of 60 meters per second using a lift blower. During this scenario, the heliostat would be put in the safe mode where the mirror is set to 90 degrees in the elevation to have the minimum amount of drag. Our heliostat survived both of these tests without any issues. For the wind test, our mirror was temporarily attached with a duct tape to test the structure of our heliostat. While the mirror aspect was not considered for this test, our team went ahead and looked at how the mirror was going to be attached. As seen in the video, under the high-speed winds, the mirror experienced flopping and bending on the corners. This led us to changing the backing of the mirror to something that would cover the whole mirror as seen on the right. And the mirror would be glued on with an epoxy adhesive to attach it.
The laser reflection targeting test was performed to demonstrate that our heliostat will accurately reflect light to distant targets. An image of the target can be seen on the bottom left of the slide. Getting the laser within the yellow circle will correspond to an accuracy of plus minus 0.5 degrees. The red circle corresponds to an accuracy of plus minus 1 degree, and the blue circle corresponds to an accuracy of 1.5 degrees. As shown in the slide, the laser reflection targeting test will be consisted of 5 different targets. The first targeting test was a human-commanded closed-loop test to hit a target with known XYZ coordinates. The second one was a closed-loop test to hit an unknown target and then compute the XYZ coordinates utilizing the azimuth and elevation angle of the heliostat. The third test was an open-loop test to hit a target with known XYZ coordinates. And the fourth test was an open-loop test to hit an unknown target given the XYZ coordinates at the time of testing. And the fifth test was an open-loop test to hit a target attached to the ceiling. The top video shows the testing for target 5. And the bottom video shows the testing for target 1. Besides hitting the 5 targets, 3 other commands had to be tested. First, the temperature and humidity sensor had to be wired into the breadboard to sense the temperature and humidity at the time of testing. The temperature and humidity will be returned in the Arduino serial monitor as shown in the image on the top left. Then, the power down command had to be tested. The serial monitor had to return a message saying, "This is the power down stub," once the power down command was entered. This command was tested, and the serial monitor returning the desired message is shown in the image on the bottom left. Finally, the danger command had to be tested to place the heliostat into safety mode. In the safety mode, the reflective surface will be configured to be parallel to the ground. This can be seen in the video.
Controls for the heliostat system are implemented in Arduino's IDE and C++. Commands were executing using an ESP32 microcontroller's GPIO pins to drive stepper drivers controlling 2 stepper motors. Many functions were created in C++ to facilitate actuation of the steppers, and mathematics were done in Python to return desired motor commands and the XYZ coordinates of the targets. The project constraints were met at this point, but no customer wants to stand by a heliostat and manually issue serial commands. To account for this, an object-oriented program was developed to control an expanse of several heliostats autonomously, far outside the scope of this class. Using the time of day, latitude, and longitude, the program determines the location of the sun in the sky. With this information and the location of a heliostat relative to a receiver, it autonomously determines the valid pointing location of each heliostat. This concept was scaled up using Python's class functionality to autonomously actuate any desired number of heliostats simultaneously upon instantiation. Each performs its own inverse kinematics and returns unique optimized motor commands, minimizing command effort to point the heliostats in their desired location, thus generating a cohesive, responsive field of self-controlled heliostats. Controls are to be deliberated via an MQTT server, which allows virtually any number of clients access simultaneously to publish and receive values. This allows for a robust, lightweight, fast, and secure control system capable of handling virtually any size of heliostat field.
So before we break down the cost to manufacture our design, there are a few components that were provided to us as a group by the lab. These items excluded from our prototyping costs are the power supply, pigtails, motor drivers, stepper motors, breadboard, mirror, and temperature/humidity sensor. Our total prototyping cost was $55.89, falling under the $110 limit set by the course, which is a reflection of the customer need 8, an overall heliostat module cost below $100 per square meter. For comparison to our prototyping cost, we use bulk cost estimates for the price for the electronics, fasteners, manufacturing, assembly, and body parts per unit for the production of 3,000 units. For the prototype, the highest cost came in the form of 3D printing filament, totaling at about 1.1 kilograms of PLA. This is directly translated to a bulk manufacturing cost using aluminum injection mold estimates, with the cost of PLA pellets proportional to our used filament factored in. The fasteners and electronic components used for the prototype and each bulk unit, the alligator clips, ESP32 controller, wires, limit switches, mirror adhesive, nuts, bolts, screws, and threaded inserts remain the same, but the cost is significantly decreased due to bulk sourcing. The manufacturing cost for the prototype is estimated at 0, as no lathe or other machining process was utilized, whereas the manufacturing cost for the bulk units is derived from the price of mold pouring and extraction per mold. The assembly cost is estimated based off of our assembly time for fastener insertion and handling of about 8 minutes, and the average hourly rate of a manufacturing technician in the United States. This breakdown yields a total cost per unit for 3,000 units of $29.84. Our design is unique in terms of its compactness and aerodynamic shape. A more compact design allows for larger heliostat fields in a limited area, and the low drag forces on our design in each mode, as well as the enclosed gear train and motor assembly, provide resistance to particulates and inclement weather, reducing risk of failure. Our heliostat is also cost efficient with our previously mentioned bulk price estimate of $29.84 per unit for 3,000 units, and it supports an advanced control schema that is reliable and scalable. We wanted to thank our industry sponsors, Northrop Grumman, Carrier, Arrigo, and Cummings, and we'd also like to thank all the TAs and our professors, and we can take any questions at this time.
Okay.
Yes, so I'll beat Tom to the punch this time. This is Rick Miles from Northrop Grumman. So I really appreciated the thorough explanation you made of the cost estimates going from 3D printing to the injection molding. But one of the things that I think is, yeah, you have some lab supplied stuff, but I would have liked to have seen that in the bulk cost as well, to kind of see what the roll-up cost was going to be when you got to mass production. But other than that, really like that. Really like the gear design as well. But when you there was a point where you discussed factors of safety, I think with your drag analysis, right? When you have really large factors of safety, don't give the actual numbers. Large numbers lead your customer to think you have over-designed the system and you're costing them too much money. Okay, so just say that you have ample margin. is a better way to discuss that. And I really like the overall presentation you did as far as talking about why you did the design the way you did. I thought you explained yourself very, very well during the presentation. So good job.
Thank you.
Man, that CFD analysis, it strikes me as insane overkill for this type of project. I've hammered on every team that does a FEM, and I'm not a CFD guy by any means, but I'll say, like, that strikes me as just extraordinarily unnecessary, especially when, as Rick pointed out, you're claiming that you've got margins of 21,000 or whatever the claim was. Do a hand calc, right? I mean, you've got pressure acting on an area, make a conservative assumption for what your coefficient of drag is and just go forward with that. CFD analysis is totally unnecessary here. When you, in your initial setup, right, you guys were saying that you had a step accuracy of less than half a degree on your gear system, and that met your customer need?
That's correct.
Can you trace that back to what the actual customer need is? Because I was just looking at the need statement when I was thinking about another group's, and you said need statement 4, right? And need 4 is mitigate optical losses due to tracking errors not to exceed 40%, and tracking errors of plus or minus 0.25 degrees are reasonable to assume, right? And I guess I'm not, a lot of teams have said, hey, we have to be within half a degree, and I'm not real clear on how that comes out of the customer requirement.
Yeah, so if I heard you correctly, it sounded like you said plus minus 0.25 degrees from what you read off that customer need. Is that correct?
Yes, sorry, I'm not real clear exactly on what a tracking error of 1/4 of a degree means. Like, do
Right,
they mean
so
like knowing the position of the sun in the sky? Like, I'm not real clear. This
Yeah.
customer requirement is baffling me the more I think about it.
Right, yeah, so I definitely feel you, because as a group, obviously especially in MEC 2, when we first handed the customer needs, the kind of first step was making sure that we understood all the customer needs correctly, of course. And if I remember correctly, the customer needs that we've seen at least say tracking error plus minus 0.5 degrees. And then in terms of the course of this class, we were given, especially with the targeting test, as you saw, the plus minus 0.5 degrees was where we were supposed to hit within this yellow to sort of meet that customer need. So in MEC 3, a lot of the customer needs, especially such as the one of $100 per meter squared, of course, since this is a prototype, that's not directly applicable, but then we were given a budget of $110 in this course. So there are certain adjustments that were kind of made to the customer needs to fit MEC 3. And the one for that customer need was this plus minus 0.5 degrees in this laser targeting test. So that's what we, that was kind of how the customer need was formed to this class. And that's what we're referring to when we're saying we met that customer need.
Okay, so then I'll ask, you're talking about the ability to point your mirror with an accuracy of plus minus 0.45 degrees, right?
Correct. Like our step size is
and given a fixed position for your laser, isn't the ability to aim the resulting laser, like the reflection of the laser, isn't that going to be double your pointing accuracy?
Sorry, could you repeat your question?
Well, I mean, your laser is going to reflect off of your target at an angle equal to the angle from the normal, right? So whatever the normal vector of your target is, the laser is going to come in and bounce off, and it's going to bounce off at an equal angle to the angle it came in.
Correct.
Right. So if your mirror is pointed by is misaligned to where you think it should be by half a degree, right, then the output beam is going to be twice that, right? It's going to be misaligned by twice that.
check something really quickly.
Yeah. So anyway, I mean, it seems like from the testing that with this configuration, you were able to meet your to target within that half-degree circle. But I sort of question the whether that was just by happenstance or what, because my understanding of the geometry of the problem is that half a degree of control accuracy on the positioning of your mirror is going to translate to a full degree of ultimate pointing accuracy.
To consistently hit the targets on multiple test setups. So I would like to do the math and like re-verify that just to make sure, because if I'm not mistaken, I think it's actually a half of that, but I like to actually check that. Give me one moment.
Sure. And then the other thing you've done was you in your analysis, you looked at like the retention of the mirror on the support, and you said, well, it's you've got more than enough area to have enough shear force for your glue. Can you explain like how the adhesive is being loaded in shear?
That was much more prevalent for the mirror design we had prior to the sort of pseudo wind tunnel testing, where we saw pretty substantial peel-in of the mirror rather than actually direct uniform lift-in force. So you can see here the edges of the mirror were exposed, and you get bend in and then production of shear force from the mirror actually being pushed along the perpendicular
like in
axis
the plane of the mirror. Yeah, the peeling tends to be where adhesives are not good, right? I mean, if you could design your ideal adhesive joint, it would be acting in shear, because adhesives tend to be strong in shear. But when you've got things trying to peel off adhesives, they tend to be significantly less strong, especially because that peeling tends to be concentrated, right? So you'll wind up with the most of your peeling stress will be sort of right at the edge of the bond, where shear tends to distribute itself sort of more uniformly along the length of the bond. So I don't think the analysis is really capturing the appropriate failure mode there.
Okay.
So given the lull in questions, I just wanted to jump in and clarify the plus or minus 0.5 and plus or minus 0.2. So these guys are working off of the fall 20, boy, what year is this? I don't even know anymore. Whatever the previous year was, fall 2021 customer needs statement, which did have the plus or minus 0.5 accuracy. We've actually dialed up the difficulty for the current group. So when you guys are interacting with MEC 2 students this semester, they have to hit plus or minus 0.25 accuracy. So that's where at least some of the disconnect with the numbers is coming from, is we ratcheted up the difficulty by increasing the required accuracy. So
pardon me. I was
Go
gonna
ahead.
say just real quickly, as I check every step the mirror goes, the angle that is reflected off of the normal is bisected in half. Therefore, for example, the mirror is moving down by 0.45 degrees at a time, it's like the actual reflected angle is moving by half of that, not twice that, if I'm not mistaken.
Pretty sure that's incorrect.
It was reflected in our tests in multiple different targeting setups, and that's the experience I've had. I can recheck, but that's what I'm saying.
Okay, well, as Carlos is rechecking, do we have any other questions or comments?
Yeah, I guess I can also comment as well, just to clarify too. With our laser targeting test, the first test was the closed loop to hit a known XYZ, just inputting steps. And we definitely saw in lab as well that, like, for instance, I don't know if you can see my mouse on the screen, the laser might be at the top of this yellow circle. And then if we were to step directly down one step, it would be maybe at the bottom of this circle, still within the yellow. So like math aside, we did see from a practical standpoint, whether it was by luck or some other mechanical something, or so, you know, we were able to do steps within that plus minus 0.5 degrees.
All right. Okay, well, so maybe just in the interest of time, unless Carlos, I don't know if you've got the, no, okay. Because now we're a couple minutes over, and to be fair, we did start a little late because I popped into the meeting late, but we might have time for like one more question, and then we can wrap up if anyone's got kind of a final closing question. No, okay, I think we're all set then. All right, so in that case, let me stop recording.